Hey guys, hope everybody's doing okay. What we're going to do right now is take a look at the beginning of our next unit, which is on intermolecular forces, matter, and solubility. Okay, so we're going to get started by taking a look at the states of matter and reviewing a little bit of that. So it'll only take a couple seconds here. So 5 main states of matter: solid, liquid, gas. The 3 we're most familiar with probably. Plasma, which is basically gas in an ionized form, so it's very, very hot. Think of the sun, stars. And then Bose-Einstein condensate, which we talked a little bit about in Honors Chem. It's really, really, really cold. Okay, so matter starts to act a little bit differently when it gets really cold, and they classify that as a separate state of matter, as that Bose-Einstein condensate. So those are our 5 main types. We're going to primarily focus on, obviously, solid, liquid, and gas throughout, throughout this unit. So, what determines what state of matter a substance is actually in? And that's where intermolecular forces come into play. Forces of attraction. So, forces of attraction between particles is one thing that determines what state of matter a substance is in. There's something else which we'll get to in a couple minutes. So, the stronger the attractive forces between particles, the more likely it will be in the solid state. So that makes sense, right? If you have particles that are relatively attracted to each other, they're going to be closer together. And if you think of our particle representations of solids, liquids, and gases, solids have their particles close together. Liquids are a little bit further apart, freely flowing, and then gases are obviously very far apart. So 2 types of solids we're going to look at. Crystalline, some notes on that. These are what you probably think of when you think of a solid. So well-ordered, definite arrangement of molecules, atoms, or ions. Think of a lot of ionic compounds for crystalline solids. Just think of table salt. That's a great example of one like this. So crystalline solids, which we're used to thinking about when we think of solids, have a really sharp melting point. So it's only over a very small range of temperatures where it'll have that, where it will start to melt and then continue to melt. The crystals are very ordered and they have a repeated structure. Think of a crystal lattice structure for an ionic compound where you have that repeating positive ion, negative ion, positive ion, negative ion. The smallest repeating unit is called a unit cell. I have a picture of that coming up. And you get a 3-dimensional stacking of these. So you get some really neat crystal lattice structures. A lot of that isn't part of the AP Chem curriculum, but it could be a little confusing, but also really cool to see how some of these ionic compounds come together and how do the particles organize themselves and make that crystal lattice. It's pretty neat. So I already mentioned sodium chloride. Sucrose, sugar is another example of a crystalline solid. Again, it's what we typically think of when we think of solids. Okay, so this is what we have with our crystalline solids, our unit cells. Okay, so we have a repeating, think of these as repeating ions here. So you might have a positive ion, positive ion, etc. You can take one repeating section, right, and that's a unit cell. So if this is NaCl, for example, here's your Na, here's your Cl, here's your next Na. Well, once the unit cell is just one piece of that before it starts to repeat. So here's one Na, one Cl, and that's it. Okay, so that's what your unit cell is going to be. The way these crystals are formed is really neat, and there are various different types of packing that are, that these ionic compounds can have, and that gives us some various, not shapes, but different crystal structures. Okay, so you don't really need to know much about those. I might link another video in the description if I could find it. But that's really about it for what we need to focus on for crystalline solids. The other type of solid is amorphous, and you can see a couple points about that. So basically the opposite of a crystalline solid. They're disordered. It lacks a well-defined arrangement that you would see in a crystal like we just saw in the previous slide. So it lacks that unit cell. And there's a very wide range of melting points here. So it might just gradually get softer instead of having a distinct solid and then liquid, and then that melting point between the two. So glass is a good example. Rubber is a great example of an amorphous solid. Okay, so That's about all you need to know here for those, the differences between those two. We're going to primarily focus on crystalline solids, right? Because we're going to focus on ionic compounds, and like sucrose is a covalent structure. We're going to talk about those two throughout the unit. Okay, second thing that determines the state of matter a substance is in, besides attractive force, is going to be temperature and pressure. So to tie that in here, to change from solid to liquid, the substance must gain enough energy to overcome those forces. So there's some force of attraction holding particles together, right? In order for those particles to spread apart more and melt, you need to supply energy for that to happen and give those particles more energy so they can move faster and move apart from one another, right? So what do we call that? That's called molar heat of fusion. Okay, so it's delta HF. So the delta is change in, the H is heat, and the subscript F is fusion. So there's going to be another one we look at in just a second. Molar heat of fusion is solid to liquid or liquid to solid, whatever that change is, okay? If you're putting energy in, it's to go from a solid to a liquid. If it goes from liquid to a solid, the energy will actually be released. So, couple different items here, and the molar heat of fusion is in purple. It gives you what it is. So you have butane, diethyl ether, water, and mercury, and it gives you the heat of fusion for all of those. So again, it's the energy required to change a solid at its melting point to a liquid, if we're putting energy in, okay? To go from a liquid to a solid, it's the amount of energy that would be released. It's the same number, but it's just a release of energy instead of energy being put into it. Why do you think mercury has such a big heat of fusion? Why is it a lot harder to take mercury as a solid and turn it into a liquid? You want to think of what we have here. Butane is just a covalent structure. Diethyl ether is a covalent structure. Water is a covalent structure. What's mercury? Mercury is a metal, right? What type of bonding is mercury going to have? Mercury is going to have metallic bonding, which is a relatively strong type of bonding, like type of force that we're going to look at, actually, I think, in the next lesson. So that's why that number is so high, 5, 7, 6, and then 23. A lot more kilojoules per mole required to melt mercury because the metallic bonding is going to have more attraction there. It's a stronger attraction, so it'll be a little bit harder to break that. Okay, we have another term here. We can go one step further, and what if we want to change a liquid into a gas? That's called molar heat of vaporization. Okay, delta HV. So we have molar heat of fusion, solid to liquid, and then molar heat of vaporization, liquid to a gas. So again, if you have a solid, you put energy into it. That's your heat of fusion to turn it into a liquid. If you're in the liquid state, put more energy into it, turn it into a gas, heat of fusion. If you're going backwards, if you're going from a gas to a liquid to a solid, the terms are the same, but energy would be released. Okay, so the particles have less energy to go from a gas to a liquid. And then if they lose even more energy, they're not going to move as fast, right? So they're going to be in the solid state. So energy goes in to the right, energy comes out as you go to the left. Now this is interesting, because if you look at this, I had these blanked out on the 2 slides ago. Look at butane. I mean, really look at all of them. You have a really relatively small heat of fusion and a pretty big heat of vaporization. So why do you think it's so much more difficult to go from, or why is so much more energy required to go from liquid to gas, which is blue here, 24, 29, 41, 58 kilojoules per mole? Why does it require so much more than to go from a solid to a liquid? We have 5, 7, 6, and 23. If you think about solids, liquids, and gases and how the particles are organized, you could figure that out. So what you should notice here is there's so much more energy required to go from liquid to a gas than the opposite, or than solid to a liquid, I should say. So let me go back. Let me go back a slide here. Okay, I like these images, okay, because this answers that question for us. I mean, look, if you go from a solid to a liquid, which we have here, is a relatively low number. Solid to a liquid, you just have to break the force of attraction a little bit, right? If you break that force of attraction a tiny bit, you're going to go from a solid to a liquid. The particles in a solid close together, right? Vibrate in place, pretty organized. Look at a liquid. They're still pretty close together. There's just a little bit less organization, a little bit more free flowing. So a tiny bit, not a tiny bit, but a small amount of energy required to go from solid to a liquid. You still have a decent force of attraction between particles there, okay? Then look, liquid to a gas. Gases really have no attraction at all, okay? Those particles have no attraction to one another. So to go from a liquid to a gas, you literally have to break every single attraction that you have between particles. So solid to a liquid, you have to loosen that attraction or weaken it a little bit. Liquid to a gas, you have to overcome all of that attraction to the point where you have a decent amount here and then none here. So much more energy is required to do that. So that's something that is good to know, and you should write down and make sure you understand why there's that discrepancy, or why is there that trend here. You know, if you're looking at the heat of fusion versus the heat of vaporization. It's all about what attractive forces are you breaking. Solid to liquid, you have to overcome them a little bit, but liquid to gas, you have to overcome them, you know, all of them, and have those gas particles basically have no attraction to one another at all. Okay, this will only take 2 seconds here. Phase changes, name review. So we have to make sure we remember what everything is here. So number 1 is solid to a liquid. You have to, what's that called? It's melting. Liquid to a gas, which is number 2. It's vaporization or evaporation. Number 3, you're going back from a gas to a liquid. Condensation. And number 4, liquid to a solid. It's freezing. And then now we have 5 and 6. So if you go from a solid right to a gas, talked about that in honors chem a little bit. Brought some dry ice in so we can play around with that. So sublimation and gas to a solid deposition. Okay, so we should make sure we are familiar with those. Okay, second part of the lesson for today, heating curve of water, or just a heating curve in general. So if you heat something up, let's say it starts as a solid. Okay, so you're going to heat something up. Temperature's on the Y, energy on the X. A lot of students think you're going to have something at a lower temperature, and then you're going to heat it up, and the temperature is going to go up in a nice linear line, right? It's actually not the case. So we're going to label the different parts of this heating curve. Let's use water, for example. So you're going to start down here. This is bad. This is not what happens. Let's erase that. Okay, you're going to start down here as ice. Okay, and then you're going to heat up ice until it starts to melt. Okay, so let's see what we have here. Between A and B, it's a solid. So this is where you have your ice cube, and you're heating it up, but it's still a solid. You haven't melted it yet. Okay, but once you do, so the temperature goes up, 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 up. And then once it starts to melt, right here at letter B, once it starts to melt, you have no temperature change. Okay, so that's pretty interesting. We'll talk about why in a little bit. Then you're going to have, at this point in time, between letter B and C, whatever temperature this is. So this is right here. If this is water we're talking about, water starts to melt, or freeze at 0 Celsius. So that is 0 right there. It's going to melt, and then eventually all of it's going to melt, right? And you're going to end up with a liquid only. If you continue to heat that, now the temperature is going to go up again. Okay? So the temperature is going to go up until it starts to what? Well, until the liquid starts to boil. So if we go over, that's at 100 degrees Celsius. Okay? You heat the liquid up till it starts to boil or evaporate, and that's what you have on that flat part between D and E. When that happens, notice how the line is a little bit longer. It takes a little bit longer for evaporation to occur, for all of that liquid to evaporate. The temperature actually does not change while water is boiling. So if you have a pot of water on your stove at home and it's boiling, the temperature is remaining at 100 Celsius or whatever it is. If you have some other stuff in there like salt, it might change it. But the temperature is not changing is the point I'm trying to make. So you can turn your stove up as high as you want. It's not going to matter. Your temperature will remain constant until all of it turns into a gas at point E. Then you can heat it up again, so you can get that gas to be relatively hot. The gas can be over 100 Celsius once all of it's in that gas state. Okay, so that's our heating curve. If you start it with water in the gas state and you cooled it down and you go back down to letter A, that's a cooling curve. Okay, it's just heating curve if you're heating it up and cooling curve if you're cooling it down, obviously. So Arya went over that. Okay, a little repetitive there. So you need to know the different parts of this curve. Okay, so you need to know what's happening at the parts where it's moving, okay, where it's increasing. The three parts where it's increasing, A to B, C to D, E to F. Kinetic energy is being added here, okay? Or the kinetic energy is increasing as energy is being added, I really should say. So kinetic energy, we need to know, is the energy of movement, right? So between A and B, you have your solid particles, okay? They're starting to move a little bit faster, right? Until they start to melt, okay? Once melting occurs, though, the temperature isn't changing. If the temperature isn't changing, there's no increase in kinetic energy. Okay, something else is occurring between B and C and D and E. The only time you have an increase in kinetic energy, particle movement, and therefore temperature, is when you have the three distinct states of matter. Okay, between A and B, C and D, E and F. What goes on everywhere else, though? Between B and C and D and E, you have a phase change. Okay, so that's important. Energy added, like the stove is still on if you're heating this up, right? Same thing over here. Energy is being added, and that goes into actually separating particles, okay, and does not increase the kinetic energy. So once you hit that melting point, all the energy being supplied is breaking the attraction, okay, between the particles of that substance. So your solid particles are moving further apart, okay, the attraction is being broken and turning into a liquid. Once the liquid state is the primary state, once that's the only state of matter you have, and you're continually heating that, now the particles can move faster, okay, and you can increase your temperature. But while you have a phase change, melting or freezing, evaporating or condensing, all the energy being supplied is not going into increasing the kinetic energy. All the energy being supplied is going into breaking forces of attraction, okay? Depends on the school year, but sometimes I do a lab where we do a cooling curve of something called paradichlorobenzene. You use it in an honors lab, in your chemical physical changes lab, if you remember that at all. But we'll cool it down, and then it'll start to freeze. We're going to have it in the liquid state. It starts to freeze, and there's a flat line, okay? Then once it's frozen, the temperature continues to go down. Okay, so you do see a really nice flat line where that temperature stabilizes. So make sure these two components here, are in your notes and you know what's going on. Okay, so I already mentioned the other thing that determines the state of matter a substance is in, besides attractive forces, is temperature and pressure. And that's kind of what we referenced here, at least in terms of temperature. Pressure makes an impact as well. This is a review from Chem 1. These are phase diagrams, right? So every individual substance has their own phase diagram. And it gives you the pressure on the Y, temperature on the X, and it tells you what the states of matter are, right? So if I have a certain temperature, a certain pressure, I can figure out where it is, determine what state of matter I have. So it's just important because students only think, or they usually just think temperature is all that matters to determine what state you're in. So attractive forces clearly matter. What temperature, it is important, but there's also the pressure aspect as well. Okay, I'll talk about that in just a little bit. We don't really need to analyze these too much in AP. That was more of an honors topic that we did. But again, some of the important points on here, there is this thing called a triple point, where you have all three states of matter existing at the same time. That's really neat. If I bring in dry ice someday, we could do a triple point lab, which is pretty cool. You can see between solid and liquid, you have your melting, freezing, and then evaporation and condensation here, and then sublimation, deposition at our lower pressure and lower temperature. Okay, so the phase of a substance depends on the temperature and the pressure, and since every substance has a different intermolecular force, every substance has their own unique phase diagram. Okay, so kinetic energy works against attractive forces to try to get the particles to spread out. Okay, so that's what we're looking at in terms of temperature here. Higher temperature, higher kinetic energy, particle movement. When the particles are moving, they're trying to spread out. So kinetic energy helps us spread those particles apart. The more kinetic energy a substance has, the more likely it will be in the gas state. Okay, more and more temperature, or more and more kinetic energy, I should say, the faster the particles are going to move, more likely they're going to be able to spread apart and go from solid to liquid to gas. The normal boiling point is going to be where you go from a liquid to a gas at standard pressure. So standard pressure for us is 1 atmosphere. If you find out where 1 atmosphere is on your phase diagram, let's say it's right here, you can go to where 1 atmosphere is, go over. Right here is where you have a transition between liquid and gas. You go down and see what your temperature is. So you can figure out what your boiling point is, like your normal boiling point, which is at standard pressure. You can find out what the boiling point is at any other pressure. So you change the pressure somehow. You can find out what your new boiling point is. So easy. Same thing with melting point. You go to 1 atmosphere of pressure. You go over to the line between melting and freezing, solid and liquid, and then you find out where you are, and you go down. It gives you your normal melting point. Notice how melting point doesn't change much with pressure. So that's the other thing we need to mention here. How much does pressure make an impact on this? I said temperature and pressure make an impact on what state of matter you have. You can see temperature has way more drastic impact. Okay, as your temperature goes up, look at how far we move. Okay, so between, this is our melting, or our condensation or evaporation point here. Huge chunk of temperature. Okay, huge range of temperatures for that evaporation or boiling point. Okay, but as your temperature changes, your melting point doesn't change that much. I mean, look, it goes from A to D. Okay, there's not a big range of temperature change at all in the melting point or freezing point. Huge range with the evaporation point. So while pressure does matter, it doesn't really matter as much for your melting, freezing as it does for even your liquid gas. So does greater pressure favor a liquid or a gas? You can take a look at the diagram and figure that out. As pressure goes up, arrow going up here, we're more likely to be in the liquid state. So why is that? So we'll kind of wrap things up here with. Particles have to break away from one another. They have to break attractive forces that hold them together to turn into a gas, right? So here's our liquid. Okay, imagine that. Particles kind of bopping around here, okay, freely flowing over one another. They're trying to escape. Okay, they're moving. They're trying to escape a little bit. And what do we have acting on that liquid? You know, imagine this is not just like a blob of it, but imagine this is like in a glass or a beaker or whatever. You have atmospheric pressure acting on that. You have atmospheric pressure pushing down on that liquid, keeping those particles where they are, right? So imagine these red arrows. These particles are trying to escape and evaporate, turn into a gas. But look, the atmospheric pressure, these blue arrows, are pushing in on that, keeping them closer together, keeping them in the liquid state. What happens if I add more arrows here? So here it's, relatively easy, I guess, to turn from a liquid to a gas, because there's not a ton of pressure pushing in, holding that liquid state down. But look, if I add more, okay, Now look, all these extra arrows, all this extra air pressure pushing down on your liquid makes it that much harder for the liquid molecules to escape and turn into a gas state. So you want to think of air pressure as pushing on the particles to keep them together. It's harder to change to a gas at a higher pressure because of all these arrows pushing in on it. Okay? You can see that here. You know, at a higher pressure, it's a liquid is favored because you're pushing in on those particles, keeping them closer together, not allowing them to escape into the gas state. Real life application of this. This is a propane tank. Okay, so you might have a propane tank for your grill, your gas grill. I mean, I have one of those. I also have a 500-gallon propane tank buried at the end of my driveway. I use propane to heat my house in the winter. I also have it also runs my water heater, but that's besides the point. The propane tank for your grill, the propane tank buried in my backyard, so I don't freeze in the winter, kind of works the same way. You know, what you have in that propane tank, if you ever picked one up that's full from a gas grill, it's pretty heavy. You're like, well, how could a gas be this heavy? Because propane's a gas, right? Well, most of it actually isn't in the gas state. Most of it's actually in the liquid state. Well, propane only has 3 carbons, so it's really, really light, and it wants to be a gas in its natural state. So how do we get it in the liquid state in that container? Well, they're pressurized, okay? So you have your propane floating around in here in the liquid state. The only reason it stays in the liquid state is you have a lot of air pressure, you know, a pressurized container pushing down, okay, on that liquid. Okay, that's why these last so long, okay, because you have the propane in the liquid state, then it eventually, like, you know, as you use up the top layer here is in the gas state. Okay, so that top here right above the liquid part, that's the part that's kind of getting pumped out, you know, and lighting on fire for you to grill, or for me to heat my house with my furnace in my basement. So some of the liquid turns into a gas and you use it. So you can, you know, a lot of, like, the liquid you have in there turns into a decent amount of gas, which is why it lasts for so long. But it's important, though, to keep it pressurized. So things that are normally gases at room temperature can be compressed into a liquid, which is how the propane tanks work. If you ever have a can of compressed air, you shake it up and it feels like liquid in there, because it is. It's under a really high pressure, and it's air under high pressure in the liquid state. You can do this, like if we're in school, I could do a quick demo of this. If you're at home, you can do this version of the demo here. One of the last things we're going to talk about is, during these phase changes, what happens to some of the energy. Okay? So, if we're in school, I could take some methanol, which is a version of like one type of alcohol, put it on a temperature probe, wave it around, see what happens. Or if you're at home, just take a drop of water, put it on the top of your hand, and just blow on it. And what do you notice? You'll probably notice that your hand feels cold. Well, why is that? That has to do with something called evaporative cooling. Okay? So to wrap up the lesson today, if you have evaporation occurring, which is one of our phase changes, really at any temperature, some molecules in a liquid have enough energy to escape. Okay? So if you have a glass of water on your table, and you come back in a couple days, there's less water in there, right? Well, how? Like, it didn't boil. Like, it's just sitting on the table. It's not boiling, right? That's because some of the water is evaporating. So remember, temperature is an average kinetic energy. So you have a glass of water sitting there, particles are moving around. The average kinetic energy isn't high enough for it to boil, but there are some particles with enough energy to escape. That's what I have here. If you look at this curve, this is called a Maxwell-Boltzmann distribution. We'll talk more about these in the kinetics unit as well. Let's just say, look at the blue line on here. You have a liquid at a relatively low temperature. Most of the particles, look at your y-axis, fraction of molecules. Most of your particles are, have that lower kinetic energy, okay? But, some particles have even less energy than your average. Let's say this is it, Okay, that's what your temperature is, because that's your kind of your average. Some are less, some are more. You do have some particles with a decent amount of energy. Whatever this is, it differs based on what substance you have. But there's a certain amount of energy required for a molecule to escape from the liquid state into the gas state. Okay? Whatever that is right here. Okay, that's the amount of energy needed. Most of your molecules, look at the fraction here, most of your molecules lie to the left of that. Okay? So most of them don't have enough energy to escape. That's why they're sitting in that glass. Some have enough energy, a tiny fraction. Look at this part that's shaded in here. That tiny amount of particles actually have enough energy to escape and turn into a gas. That's evaporation. Okay? When a liquid evaporates, these particles with that higher energy amount leave. What's left? Energy, or particles with a lower energy value, right? Or a lower energy amount. So if you're left with particles that are moving slower, that's why evaporation is a cooling process. So when you're in some athletic event or whatever, you're stressing out, taking your AP Chem test, and you're sweating, you're feeling a little bit cooler. Sweating cools you down because you have sweat on your skin, right? The sweat evaporates, and evaporation is a cooling process because the higher energy particles of your sweat are leaving. You're left with lower energy particles after those higher energy particles have gone. Okay? So that's what this diagram is showing you. You have water, you have particles moving around, bopping around down here. You have some that are able to escape, and then what you're left with is a cooler temperature. Real-life applications to this are everywhere. So sweating, like I already said, is a cooling process. It's how your refrigerator works. I might link a video on my YouTube channel or an Edpuzzle if we're watching this there that explains that. But it's literally how your refrigerator works. You have a compressor in your refrigerator, and you have something called an evaporator coil. So you have this liquid, okay? The liquid evaporates, okay? Evaporation is a cooling process. We just talked about that. So as the liquid evaporates, that's cold. You hear a fan kick on in your refrigerator. That fan kicks on, and it blows that cold air around your refrigerator. Makes everything cold. Well, what happens to that gas? Well, that gas, that substance that evaporated, has to turn back into a liquid. Those are your condensing coils, usually found on the back of your refrigerator. If you ever noticed, they feel hot, they feel warm, because condensation is a warming process, okay? So to go from a liquid back into a gas, energy has to be released, okay? So that is going to be a warming process. That's why it's important on the back of your refrigerator to keep, the 6 inches of dust that's going to form off of those coils, because they can get, get hot. It could be a hazard, right? And it could decrease the efficiency of your refrigerator as well. Air conditioning works the same way. So my air conditioning unit is in my, behind my house. It kicks in. There's some evaporation that takes place. Evaporation is a cooling process. My furnace, or like the fan, in my basement, kicks on. It blows the air around my house, that cold air. And in my AC unit in the back of my house, it's it's where that condensation occurs to turn that liquid that evaporated, that coolant that evaporated, back into the liquid state, so it could evaporate again and cool my house. So evaporation is cooling, condensation and freezing is warming. One final application here to wrap this up is orange ice prevention. So I have a picture of it here. If there's going to be a frost, and farmers want to protect their oranges from that damaging frost, it seems contradictory here, but it's not. They'll actually go outside, they'll spray down their orange trees, so when it gets cold, ice will form on them. You're like, why on earth would that happen? The ice actually protects the oranges from the environment. And freezing, right here, is a warming process. So it actually warms the oranges. And it doesn't make any sense. How's that work? If something freezes, you go from a liquid to a solid, right? Solids have less energy. So for a liquid to go to a solid, it has to lose energy. Where does that energy go? It goes to the orange. All right? So it actually warms it. So this is pretty neat stuff, I think. If you're melting, melting is, freezing is a warming process. Melting is a cooling process as well, because you need energy put in to take a solid to a liquid. So it takes energy from the environment. So it's a cooling process as well, even though it doesn't seem that way. Anyway, that takes care of this, I think. Yeah, so we're good to go. That takes care of the first main lecture of this unit. And we'll just kind of build on some of this stuff as we go through. Okay, guys? If you have any questions, let me know. That's about it. Thanks.